So this is going to be about relativity and the emergence of time. Anyone who's been questioning what is time, where time is coming from, relativity has an answer to this, and it's actually quite straightforward. The math here is just algebra, so don't be too intimidated by it. There's no really high-level complex math to get there. All we're going to do is take Einstein's thought experiment and go a little bit further. And I'm sure there's way further that we can go, but this is just going to be like a first attempt to unlock some secrets to the universe. So let's get started. So just a quick review, Einstein's thought experiment. We've got this laser cavity with a laser going at the speed c to the other end, and then it's going to reflect. It's going to reflect back and forth within this cavity. I'm just going to run forward a little bit because this is meant to be quick. So if we change the frame of reference, so we've got these two speeds, components to speed, and here we work out the speed it goes across the length is equal to the square root of c squared minus v squared. And then we have two frames of reference, the t prime frame, right, the new frame of reference, how much time it takes for it to bounce back and forth. And then we get this formula for what the change in time is. And then we can keep working on the formula, and this is our end result here. So the difference in the new frame of reference is equal to the change in time in the old frame of reference divided by this gamma factor. So what are these implications? So here's a new formula. What are the implications? When the change in velocity, right? We're talking about change in velocity because it's always relative to something else. So we're looking at ourselves as like this standard observer, and then this thing is moving away from us, so we're the ones observing it. When v is zero, when it's not moving, when it's staying static, the time advances as normal, obviously. But when the speed gets really, really fast, the time takes longer. The clock takes longer to tick. And so we're saying time is slowing down. Yeah, it takes an infinite amount of time for the clock to tick all the way. So something moving at the speed of light does not advance in time. So only something that is localized will have time. Anything that is non-local, that is completely all in space, will advance in time. So let's go a little bit further. Here we see X and Y. We don't need time in order to map light. All we need is space, because light is entirely in space. It does not advance in time. So the time it takes to do one tick is infinite. It never does one tick. It does not experience time. Light is only in space. Okay, so localization leads to time. Only when you slow something down does time actually emerge. So localized harmonics store energy. So we see this all over the world. How do you store energy? What is the energy storage mechanism? It's localized harmonics. We have energy stored in the rotation of the planets. We have energy in molecules, in the vibrations of molecules, and heat. And heat stays, right? Heat dissipates eventually, but it has a duration. It has time. It doesn't just vanish. So localized harmonics, we have localized harmonics in atoms, and string theory also theorizes this localized harmonics going on. So it's not a big leap to think that there's some kind of localized harmonics with particles. String theory is already theorizing this. So let's just go with this. Most basic localized harmonics that we know of is a quantum well. We have all of these energy levels within the quantum well, and it's able to store energy based on these energy levels. And if ever wants to go up an energy level, it has to absorb energy, or if ever wants to go down an energy level, it has to emit energy. So let's say light is in this cavity, this laser cavity, and it's able to go back and forth, which means it is now localized, which means light is no longer in space, it is now in time. So localized energy persists in time, it advances in time, whereas non-localized energy doesn't reflect, doesn't go back and forth, so it doesn't advance in time. The phase that it's at will always be the phases that it's at. Here, it will stay in a local spot so it can tick forward. And so we have two localized forms of energy here, two localized wells. And what happens is time emerges as one well ticks in relation to the other well. That's how time emerges. So when one is moving, the other one is staying still, we have two frames of reference. Time emerges as a relationship between localized harmonics. Okay, let's go a little bit further. Okay, so this is the standard relativity equation that everyone knows, But there's actually a second part to this relativity equation. And so let's analyze this equation a little bit. For massless particles, so when there is no rest mass, like light, this is the entire part. E equals pc. So all of the energy of light is in its momentum times c. And so this is a spatial component. And for particles at rest, when something does not have any motion, it's all the rest mass. And it has time. So here, when it's all in this form, there's no time. And when it's all in this form, there's only time. There's no space. And so when we want to analyze this equation, we have the momentum energy in space, and we have the rest mass energy in time. Two components to the energy. And if you look at this equation before, it looks very similar to this. Like these are very similar equations. Let's take momentum that has no mass. We say it has an effective mass. Light has an effective mass. Why? Because it has a momentum. When we calculate out the momentum, we have the energy of the light is equal to c squared times this effective mass. We have this E equals h bar omega. And so then we get to the effective mass is equal to this for light. So light has an effective mass. Okay, so let's talk about these particles. These particles also have a rest mass, but they also have an effective mass. The rest mass of the molecule is greater than the total of the rest mass of all of the particles. So what's going on? Why is the rest mass of the molecule greater than the rest mass of all of the constituent particles? Well, there's binding energy. There's extra energy there, and that we take and contribute to the rest mass. We add that to the rest mass. So really, rest mass seems to all just be an effective mass, right? How do we know there is such a thing as rest mass? And it's all not just effective mass. Let's say, okay, that was the molecule, but let's change it to a particle, the mass of a particle. What's the mass of an electron? What's the mass of a quark? Well, it's greater than the sum of some masses, maybe. Maybe there's something going on. And so let's talk about these relative harmonics. Let's say there only is an effective mass, and it's the sum of all of these harmonics. So we can add a velocity here, and because rest mass is invariant for all observers, the omega must remain constant. C squared is invariant, h bar is invariant. The only thing that changes is its frequency. And if we start accelerating it, the mass would change if the frequency changed. So the frequency has to stay constant in all frames of reference for this rest mass. This it's an effective mass, but it looks like a rest mass to remain constant for all observers. Okay, that's interesting. So as time slows down, it takes longer for the light to bounce back and forth. That means this frequency has to go down. Therefore, to maintain the same frequency, the cavity must shrink. You must get something called length contraction. It keeps the frequencies locked and the rest mass invariant. So we know that the rest mass is invariant, so the frequencies must stay the same no matter how fast it's going. Okay, so what are the internal harmonics of particles? All right, so we just guessed at this quantum well, what is actually going on in these particles? That's why we have all of string theory to talk about what is this harmonic state of the particles. So let's speculate. Why not? So let's take this standard model. We know we have this standard model of masses and charges and all of this stuff, and it's all well documented in spins. And let's just say this mass is an effective mass, and it's the sum of these frequencies. Let's just say that's where the mass comes from. So it's just a first idea. Like this is like the Bohr idea of the atom, right? Just this first idea of how do these particles work? So let's just take the first generation. We saw that there are many other generations. We have first, second, and third, and first, second, and third generations. So we'll just look at the first generation for now because we're trying to develop this Bohr model. What we have is the electron neutrino and the electron antineutrino. They don't have any charge, and they both have the same masses, just they annihilate when they meet each other. One is the opposite of the other in some weird way. What does that way even mean? This is the mass. And so this mass we see here is in a similar form, electron volts per c squared. And so we get the omega is equal to 0.2 electron volts divided by h bar. That's simple. What about the positron and the electron? Well, here we've got a spin, and here we've got a greater mass. And so what are we going to say? Let's just say that it's equal to the sum, right? The sum of 511 kilo electron volts, right? This is kilo electron volts divided by h bar is equal to the sum of two frequencies or more frequencies. I don't know how many frequencies are in there, but now we're getting to where the mass might come from. And okay, we've got these quarks. So let's say it's the sum of three frequencies or more. And so every time we get a higher particle, we get a higher excitation of energy. We get an extra energy level within that well. And then here there's the up and anti-up, right? They've got different charges. And so we're going to have to also explain that charge. Why is that charge coming in fractions? So let's look at momentum mechanics. So according to the standard model, forces are the result of momentum transfer. There's no actual such thing as a force. What's actually changing is this energy is going to momentum. So we are transferring momentum, we are causing motion. The sum of momentum transfers over time is acceleration. So these forces are the result of momentum transfer, not the other way around. And we have, when we map momentum from 0 to infinity, momentum can be 0 to infinity or minus infinity, right, to infinity. We're actually mapping velocities from 0 to c because we're normalizing momentum. We're normalizing momentum between 0 and infinity, mapping it onto 0 to c on velocities. Velocity is emergent from the normalization of infinite momentum. So momentum exchange is dependent on phase difference? Question mark? Is that what's going on? Maybe this is the mechanic. So we have this phase difference between two particles, and we're just talking about the same energy level. So on the first energy level, there might be a phase difference between these two particles. Is the momentum transfer related to the cosine of this phase difference? So if we have just two spaces the particle can be on, we have this phase difference is 2 pi over n. So if n is 1, we have the full 2 pi. That means it's at the same spot. That means the cosine of this is fully repellent, like repels like. If we have n is 2, it's pi, it's half, it goes on the opposite side. They're opposing, so here we get like plus and minus signs. And these ones attract. The opposite attracts based on this formula. Okay, that's an interesting relation. What happens when so this is the standard one. This is the two sides. And then when we have three, we get this model where each one repels the same, but it attracts everything else. And this is what quarks do. Quarks attract the other colors, but they repel the same color. Pi over 4, here we get angles that don't attract or repel. We get the 90-degree angle where the momentum transfer is 0. So this is interesting. This might be where two electrons can occupy the same state without affecting each other. And the pi over 6, this makes more sense for quarks and antiquarks because now you have the antiquarks. You have the opposites that can attract. The antiquark attracts the quark. So this phase difference model actually maybe even simplifies QCD and QED, quantum electrodynamics and quantum chromodynamics, which is how we decipher particles, how we develop, how we explain the standard model. Okay, so yeah, I added the cosine here. So the cosine here is 1 or minus 1. So repulsion or attraction at lower levels, right? So in here we have repulsion, attraction, and then 0 is nothing. And here we have the same thing. So the quark antiquark will have a strong attraction. All in all, it looks like they balance out, right? 1 minus 0.5 minus 0.5 is 0. These are all the quarks. They actually add up to 0. This is where color comes in. We're saying all color has to be white. No, electron and positron balance out by 1 and minus 1. That can become 0. What we're looking for is this nullification. And same thing, quark and antiquark become 0, 1 and minus 1. So this sort of maps out kind of perfectly to quantum chromodynamics. So here we have this 6. So we have the 6 colors. We have red, green, and blue. And the anti-red is cyan. We don't call it cyan, we call it anti-red, but technically we could look at it as colors. It's cyan. The anti-green is magenta. And so the quark colors kind of emerge from this sort of pattern. Okay, so shared harmonics. One more thing we can add to what's going on here. A larger well has a lower base frequency. If we increase the size of the well at that energy, You see this well here on the side. Well, if the energy level is above this threshold, got this particle and this particle, then the frequency can show up here across this whole thing, meaning it could have an actual lower frequency. It doesn't have to be constrained at a high frequency because of the walls. It can be a little bit more free, meaning that it takes energy to separate them, because once you separate them, the energy has to condense itself, has to increase its frequency to be contained within a wall. So when energy is shared across several wells, it can reduce its frequency. Separating those wells again would require an increase in energy. The same frequency could have different energy levels depending on the ground state of the potential energy well. And then another thing is, okay, so let's say you're increasing this energy, increasing this. In order to separate these particles, you have to increase this energy so much. Where does that energy go once it's completely separate? Well, the energy goes into the separating the energy, into increasing its frequency. But two, that energy doesn't like to be in that well. It likes to share. So that energy has to be enough to create a pair in order for it to share energy with a pair. This is what happens in quantum chromodynamics. If you're separating a quark from a hadron, you're separating this quark away. It actually forms a new antiquark in order to share the energy. So so you don't actually have to increase its energy so high to separate it. You have to increase its energy high enough for it to create an antiquark, so that it can still keep sharing its energy. So, okay, one last little thing on potential and kinetic energy. So we see potential and kinetic energy doesn't have this square component to it. There's something going on where it's just a sum of energy. And this is like the standard way. So what's going on? Where's the mismatch? Energy in time, we have energy in space, and here we have energy sort of mapping, right? Potential is kind of less in space. Kinetic is more in space, right? There's more motion in kinetic energy, less motion in potential energy. So let's try to resolve this by saying, okay, let's say this energy is the sum of all of the potential energies and the sum of all of the little kinetic energies going on. And let's quantize these energies. So if you quantize these energies, meaning this can only be potential or only kinetic, there's no in between. Before we had states where we have an in between state. We can have a something with a rest mass moving. So we can quantize it. Let's say there's a quantize. And so what happens is if you have 0 and 1 both squared, or 1 and 0 both squared, it looks like simple addition. So really, it looks like a plus, but it could be because this energy is quantized. So that's just a question mark. It's one possible solution. Maybe there's another solution out there and someone could figure it out. Or maybe it's just two different kinds of energy, right? Maybe there is a solution there, but it's just something I was trying to solve while going through this. Unity. In the physical world as we know it, unity is not a primary, but rather an emergent property. This implies that separation is fundamental, a necessary condition for phenomena such as information and computation. Even time itself arises from the changing relational phases of energy. Consequently, relationships, existing on all levels, reveal themselves as the most fundamental aspect of reality. Our concept of unity thus transforms from that of a static objective backdrop into something more akin to the harmony of gears in a clock. All creations, in a similar vein, achieve their form by combining distinct parts of reality into a synchronized emergent behavior. Thanks for watching, and have a good one.